The life cycle of fuel for nuclear fission reactors begins with the mining of uranium ore, the chemical extraction of uranium, and its initial processing. For the fuel of most power reactors, its enrichment follows. In other words, an increase in the proportion of the fissile isotope uranium-235. The next step is the actual production of fuel pellets, rods, and assemblies, depending on the type of reactor for which they are intended. After fresh fuel is brought into the reactor, its fission releases energy for several years, which is used to produce electricity. Spent fuel is temporarily stored and cooled in intermediate storage and reprocessed. The life cycle of nuclear fuel is completed when it is permanently stored in the final deep repository. Nuclear fuel can be any material capable of releasing energy through nuclear fission or fusion reactions. In theory, almost all isotopes of elements from the beginning of the periodic table could be used as fuel in nuclear fusion, and isotopes of elements from the end of the table for nuclear fission. However, only some of them can be found or produced in sufficient quantities, and their nuclear reactions are energetically advantageous. Deuterium and tritium isotopes of hydrogen best suit such conditions for fusion. Fission has been practically based on uranium and plutonium isotopes for several decades, but thorium isotopes are also being considered in the future. Uranium is an element that is abundant in the Earth's crust and in the world's oceans. For nuclear energy, the fissile isotope uranium-235 is important, which unfortunately is only 0.7% in uranium ore, and its proportion in the fuel must be increased by complex enrichment processes. The predominant isotope of uranium-238 is also useful, because it produces the fissile isotope plutonium-239 by neutron capture in the reactor. In addition to plutonium-239, the plutonium-241 isotope can also be used as nuclear fuel, which is also created artificially by the interaction of a neutron and the atomic nucleus of plutonium-240. The use of plutonium in the role of nuclear fuel is a bit more complicated compared to uranium fuel. The reason is the artificial origin, the high toxicity of plutonium and its compounds, and the lower safety of plutonium-burning reactors. When comparing the energy potential of nuclear and conventional fuel, we can start from the assumption that the fission of 1 kilogram of uranium-235 nuclei could theoretically release 10 to the 11th kilojoules of energy. The synthesis of light elements is better by order of magnitude, in which up to 10 to the 12 kilojoule can theoretically be obtained from 1 kilogram of fuel. In practice, however, the use of nuclear fuel is much lower, and modern fission energy reactors are able to obtain approximately 5 times 10 to the 9 kilojoule of energy from 1 kilogram of fuel enriched to 4% uranium-235. Compared to the calorific value of coal of 10 to the 4 kilojoules per kilogram and the calorific value of hydrogen of approximately 10 to the 5 kilojoules per kilogram, it is still clear that the kilogram of nuclear fuel can provide us with several orders of magnitude more energy than conventional fuels. The basic division of nuclear fuel must of course be the division into fusion fuel and fuel for fission reactors. Fusion reactors, which are still only in the development phase, generally include isotopes of light elements, such as deuterium, tritium, and helium. Fission reactors, which are relatively widespread around the world, on the other hand, can easily handle fuels with nuclei of isotopes of heavy elements, mainly uranium, plutonium, and thorium. By enumerating the elements, we arrive at the second type of division of nuclear fuel, according to the predominant element making up the fuel, or a mixture of elements, as in the case of MOX fuel. From a physical point of view, nuclear fuel can be further divided according to different parameters. Probably the most important division is according to the enrichment of the fissile isotope. In special types of heavy water reactors, nuclear uranium fuel can be used without costly enrichment at its natural uranium-235 concentration of 0.72%. The most common enrichment of a fissile isotope in nuclear fuel ranges from 2 to 5%. With such enriched fuel, most nuclear power plants work with one of the thermal types of nuclear reactors. Enrichment from 5 to 20% is typical for research and experimental reactors. Some research reactors may require even higher than 20% fuel enrichment, but in most cases, high uranium-235 fuel enrichment is typical for fast reactors. Another parameter for dividing the fuel is its chemical form. Historically, the metal form of fuel is the oldest. It was already used by Enrico Fermi in his first Chicago pile. But the vast majority of nuclear fuel used in current power plants has a safer form of oxide. In the phase of experimental tests, nuclear fuels are based on carbides or nitrides. These forms are likely to find use in high-temperature fission reactors in the near future. The most frequently used type of fuel in nuclear energy today is solid, slightly enriched oxide uranium fuel in the form of small pellets with a proportion of up to 5% fissile isotopes. When we look at the nuclear fuel cycle as a whole, it can logically be divided into two parts: the part for using the fuel in the nuclear power plant and the part dealing with what to do with the fuel after its energy use. The first part includes the complete production of fuel from ore extraction and primary processing, through enrichment and production of fuel assemblies, to transportation to the nuclear power plant and loading into the reactor's core. The second part includes temporary storage of spent fuel assemblies, possible reprocessing of fuel, and methods of its final storage in deep geological repositories. Uranium is relatively abundant in the Earth's crust, and uranium ore deposits are found practically all over the world. The ore is mined either in classic surface mines, deep mines, or by the in situ leaching method. The mined ore is crushed and ground, and the uranium is then chemically extracted and concentrated into uranium oxide, known as yellowcake because of its color. This oxide contains 60 to 70% uranium. The next step in the production of nuclear fuel in the first part of the cycle is to increase the concentration of the fissile isotope uranium-235. This process, called enrichment, is based on physical principles because chemically both isotopes of uranium are the same. They differ only in the tiny mass of the 3 neutrons, which is why their separation is very energy and time-consuming. There are several ways to enrich uranium. The oldest ones use a Calutron, working on the principle of a mass spectrometer, or a semi-permeable membrane through which uranium hexafluoride gas is repeatedly forced through. The most widespread method of uranium enrichment uses centrifuges. Uranium hexafluoride gas is spun in them at a relatively high speed, during which the slightly heavier uranium-238 is pushed to the edge of the centrifuge by centrifugal force, and the lighter uranium-235 remains closer to the center. The latest method of uranium isotope separation is based on the excitation of only uranium-235 with a precisely tuned laser. Small cylindrical pellets are pressed and baked from the enriched uranium oxide powder in the next stage of the cycle. Several hundred of these ceramic pellets enclosed in a 4 to 5 meter long hermetic jacket of zirconium alloy form the fuel rod. The bundle of fuel rods is then used to make a fuel assembly, the basic unit designed to safely handle nuclear fuel in a power plant. Each type of reactor requires its own type and size of nuclear fuel, which is why fuel assemblies are manufactured exactly to measure for each specific reactor. The last place falling into the front end of the fuel cycle is the nuclear power plant. New fuel assemblies are transported in protective containers from the production plant to the fresh fuel storage in the power plant, and during the fuel exchange, they are put into the reactor core by a loading machine. The average time the fuel is in the reactor is 4 years, during which the fission reaction takes place in the fuel and the energy is released. By removing the fuel from the reactor, it becomes spent fuel, and by storing the fuel assembly in the storage pool, the nuclear fuel enters the second, back end of the fuel cycle. The back end of the nuclear fuel cycle can have 2 distinct scenarios. In the first, the spent nuclear fuel is temporarily stored in an interim storage, and after the radioactivity has decreased and the heat production has decreased, it is directly deposited in a deep geological repository. We call it an open fuel cycle. In the second scenario, the fuel is reprocessed sometime after it is taken out of the reactor. Uranium and plutonium are extracted, which are then used to make new fuel. Reprocessing is thus linked to enrichment and fuel production, and in this case, we speak of a closed fuel cycle. After removal from the reactor, nuclear fuel is most often stored in water pools in close proximity to the reactor. It is highly radioactive and still generates a lot of heat at this stage, so the pool water ensures its continuous cooling and also acts as a shield against ionizing radiation. After 3 to 4 years, when the radioactivity of the fuel is reduced by about half, the fuel can be transferred to another interim storage, where it can remain for decades, or it can be taken for reprocessing. Intermediate storage facilities for spent nuclear fuel can be wet or dry. In the wet interim storage, the individual fuel assemblies are constantly cooled by circulating water, similar to the reactor pool, even though the cooling requirements are no longer so high. Dry interim storage requires significantly easier maintenance. The cooling of the spent fuel in them is ensured by the natural circulation of the surrounding air. In dry storage, groups of fuel assemblies are hermetically sealed in special steel storage containers, and these are spread out either in the open air or in light, well-ventilated halls. Alternatively, dry fuel assemblies can be placed in thin-walled closed containers and then stored in special concrete cellars and containers. A closed fuel cycle is characterized by the reprocessing of spent nuclear fuel. This complex but useful process is beneficial for two main reasons: obtaining up to 25% more energy from the spent fuel and reducing the amount of high-level waste by up to 80%. By reprocessing the spent fuel, uranium and plutonium isotopes are gained, which can be reused with some limitations in the production of new fuel. The main method used in reprocessing plants to extract uranium and plutonium is the Purex method, in which chopped fuel rods are dissolved in nitric acid and the useful isotopes are then separated from the unwanted fission products by various chemical reactions. These are eventually processed through the vitrification process into highly active glass, which is then disposed of as waste. For highly radioactive waste, which is expected to emit dangerous radiation for thousands of years, it is necessary to build a deep repository in a stable geological formation. It should be a site with no groundwater and no danger of earthquakes, tsunamis, or inundation by seawater or lava, and should provide natural barriers to prevent accidental release of radionuclides into the environment. Work on final repositories is underway in many states, but none have yet begun to store spent nuclear fuel.